Okay, let's dive straight in. Consider this. At some mining operations, a single hour of unplanned equipment downtime can cost upwards of $100,000.
Wow.
Yeah, think about the sheer scale and the relentless pace. So for anyone wanting to get a real edge in understanding how this crucial industry avoids those kinds of financial earthquakes, without getting totally lost in the weeds, we're taking a deep dive into predictive maintenance in mining.
Hmm.
This isn't just about fixing things. It's like seeing the future of your machinery.
Exactly. And we've pulled together a really comprehensive set of perspectives for you on this.
Really?
Our sources, they range from sharp insights from tech innovators like CSM Technologies and DataMine AI, through the kind of broad industry lens of Mine Australia, to the practical, boots on the ground knowledge from UE Systems.
Okay.
We've also got an environmental angle from Earth Sciences Pakistan and a specific, quite challenging application down in Argentina's Vaca Muerta region, thanks to a report from HubTech IA. So it's a real full spectrum view of how things are changing.
Absolutely. Our mission today is laser focused, really, to extract the core intelligence on how predictive maintenance, especially when it's supercharged by AI and machine learning, is fundamentally reshaping mining.
Right.
We're talking tangible wins, both in operations and, well, profitability. And we're committed to delivering these insights in a way that's clear and hopefully engaging.
Hmm.
So let's get down to brass tacks. What exactly is predictive maintenance?
Okay. Well, at its heart, predictive maintenance, or PDM, as you'll often hear it called, is about being proactive. It's a strategy that uses real-time data and advanced analytics to anticipate when a piece of equipment might fail.
Right, anticipate.
Yeah, this foresight, it allows for maintenance to be scheduled precisely when it's needed, before a breakdown actually happens. It's a pretty significant departure from the older, more reactive approaches.
Right, because I think most of us can picture the old scenarios. Either something just breaks down, causes chaos, and a hefty bill.
Yep, panic stations.
Exactly. Or you have these routine checkups, scheduled maintenance, regardless of whether a machine actually needs attention at that point. What are the real downsides there compared to this predictive way?
Well, reactive maintenance, just fixing things after they break it, inevitably leads to unplanned downtime, which, as we just said, can be incredibly expensive in mining.
Astronomical costs.
Yeah, and the repairs themselves are often more extensive, more costly, when a small issue is allowed to snowball into a major failure. Preventative maintenance, on the other hand, which seems better in theory, it operates on these fixed schedules, based on time or usage hours.
Like changing your car oil every 5,000 miles kind of thing.
Exactly like that. But the problem is equipment wear isn't always that predictable, especially under harsh mining conditions. So you could be spending time and money maintaining something that's actually perfectly fine.
Wasting resources.
Wasting resources,
Zero.
manpower, yeah. Or, conversely, your schedule might completely miss the early signs of a developing problem. So predictive maintenance aims to be far more efficient, much more targeted.
So how does PDM actually get that foresight? What kind of signals is it looking for to, predict trouble ahead?
It draws on a really rich stream of data. The most common inputs are from sensors, things monitoring vibration, temperature, pressure, even acoustic patterns, noise.
Okay.
Think of the complex vibrational symphony of a massive haul truck. Neural networks, for instance, can be trained to spot tiny deviations in that symphony, a slight change in a specific frequency that maybe a human might miss, which could indicate a developing fault in a critical bearing, maybe weeks before it becomes really obvious or measurable by traditional methods. That gives you that crucial early warning.
I see.
Then there's the historical data from past maintenance. Records of previous failures can reveal recurring weaknesses, patterns of degradation, and crucially, machine learning models analyze all this information.
Right, the ML part.
Yeah, and these predictive systems are often integrated with broader asset performance management systems, APM systems.
Okay, APM, what's that briefly?
Yeah. Think of APM as the kind of overarching strategy. It's about optimizing the life cycle and performance of all the mining company's assets. PDM is a critical tool within that bigger APM framework. It provides the real-time health insights that then inform those broader decisions about scheduling, about capital expenditure, overall operational efficiency.
Got it.
The ultimate goal is just catching those early whispers of mechanical trouble so they can be addressed proactively.
Okay, so this proactive approach, fueled by all this diverse data, aims to foresee failures. Now, why is this so incredibly critical in the mining sector specifically? I mean, it sounds beneficial anywhere,
Yeah.
but you emphasize the high stakes here.
The stakes are, well, they're exceptionally high. Mining operations are fundamentally built on the reliable operation of incredibly complex and very expensive machinery.
Right, big kit.
Oh, yeah. We're talking colossal equipment like drag lines, those enormous excavators stripping away overburdened haul trucks the size of small houses, crushers that just pulverize rock, vast networks of conveyor belts.
And all working in tough conditions.
Exactly. Punishing conditions, immense stress, constant bombardment by dust, vibration, often extreme temperatures. It's a constant battle against wear and tear.
So when one of those goes down unexpectedly,
The repercussions can be massive, financially devastating, and that's precisely where the advantages of predictive maintenance become so compelling.
lovely.
First and foremost, it dramatically reduces downtime. By detecting potential problems early, maintenance can be scheduled during planned stoppages, minimizing those really costly interruptions to production.
That makes perfect sense. If you can see a component is nearing failure, you slot in a replacement during routine maintenance instead of a sudden, halt to the whole operation. What else? What other key benefits does PDM offer here?
Lower maintenance costs, that's a significant driver. Addressing minor issues early stops them escalating into major repairs, which always involve higher costs, parts, labor, maybe emergency call-out services.
Right.
There's an example, Votorantim Cementos, a big player in cement and mining, they reportedly achieved $5.5 million in savings by implementing Aveva's predictive analytics.
Wow, $5.5 million. That's substantial.
It really puts the potential ROI into perspective, doesn't it? And sometimes these systems can also help optimize the maintenance schedules themselves, leading to more efficient use of resources overall.
Okay.
Then there's extending equipment lifespan. By only intervening when necessary, you reduce that unnecessary wear and tear, allowing these incredibly expensive assets to operate for their intended lifespan, maybe even longer.
Preserving the capital investment.
Exactly. Safety is also paramount, obviously. Preventing catastrophic equipment failures is a top priority in mining. Personnel safety is always number one. Datamined AI estimates their systems can contribute to something like a 42% reduction in safety incidents related to maintenance activities.
That's a huge safety improvement.
It really is. And finally, predictive maintenance allows for optimized spare parts inventory. By forecasting when parts will likely be needed, companies can manage their stock more effectively, reduces the costs of overstocking, and avoids the delays caused by frantic last-minute orders.
Right, having the right part at the right time, but not tying up capital unnecessarily.
Precisely.
So PDM offers this really compelling suite of benefits. Now let's dig into the technologies making it happen. We've mentioned AI and machine learning quite a bit. How are they specifically revolutionizing predictive maintenance in mining?
Well, AI is truly transformative here. It gives you the ability to collect, store, and crucially analyze the enormous volumes of data generated by modern mining operations.
Just the sheer scale of data must be immense.
It is. Think about the number of sensors on all that equipment constantly feeding back information. Without AI, making sense of this data in a timely, actionable way would be, well, virtually impossible.
Right.
Your traditional manual condition monitoring systems, they just can't cope with this scale and complexity. They often miss those rapidly developing faults because they aren't continuously processing and learning from the data streams.
They're too snapshot-based, maybe?
Oh. Kind of, yeah. And this is where AI-powered sensor fusion technology, like the stuff used by Razor Labs' DataMind AI, becomes critical. Tomer Stulovich from Razor Labs, he highlighted the inherent challenge of integrating data from these historically isolated monitoring systems, each sensor telling its own story but not connected.
So sensor fusion brings it all together. Instead of these separate silos of information, you get a unified view.
Precisely. And it's more than just putting them side by side. Imagine you have separate temperature and vibration readings. Sensor fusion uses sophisticated algorithms to analyze how these readings correlate.
The relationship between them.
Exactly. So maybe a slight increase in temperature along with a specific change in vibration frequency in a certain type of bearing, that might be a much, much stronger indicator of impending failure than either reading looked at in isolation.
I see. That makes sense.
That's the kind of synergistic insight sensor fusion provides. It combines data from various sensors, vibration, temperature, pressure, oil analysis, even visual data sometimes, to build a much more holistic picture of equipment health. Strilovich emphasizes this multi-layered approach can uncover failure patterns that would just stay hidden if you were only looking at a single data point.
Okay, so you get a richer, more nuanced understanding by looking at the interplay of different factors. And then it's the machine learning that takes this fused data and actually does the predicting.
Exactly right. Machine learning algorithms, and there's a whole toolbox. Things like neural networks, decision trees, support vector machines, clustering algorithms, time series analysis. They sift through the sensor data to identify anomalies, track the subtle evolution of equipment health over time, and even estimate the remaining useful life, the RUL, of critical components.
RUL, remaining useful life. That sounds incredibly valuable. So what are some concrete ways these algorithms are being applied? Give us some specific examples of the kinds of insights they provide in mining.
Sure. Neural networks, for instance, they really excel at detecting those subtle, nonlinear patterns that might indicate early stage degradation, those hidden failure precursors we mentioned.
Okay.
Decision trees can be used to build diagnostic models, helping to pinpoint the specific cause of an anomaly once it's been detected.
Like a troubleshooting guide?
Sort of, yeah, an automated one. And as we discussed, sensor fusion, powered by ML, combines these diverse data streams for much more accurate and timely failure prediction. Data mined AI, for example, they claim their system can detect faults up to 21 days earlier by analyzing these complex vibration patterns.
21 days, that's a significant head start.
It is, and what's particularly insightful here is that these algorithms can be trained on historical failure data. They learn the specific signatures of different types of failures in different pieces of mining equipment, so they can identify patterns that might be too complex or too subtle for human analysts to consistently spot.
That early warning capability sounds incredibly valuable. What about other advanced concepts like digital twins? Where do they fit into this predictive maintenance landscape?
Digital twins. They're essentially virtual replicas of physical assets. Could be a haul truck, could be an entire processing
A
plant,
computer model.
a very sophisticated dynamic computer model, yes. When you integrate them with AI and machine learning, it creates this powerful environment for simulation and analysis. Mining companies can test out different operational scenarios, predict the impact of various maintenance actions, even simulate potential failure modes without risking any damage or downtime on the actual physical equipment.
This is like a virtual test lab.
Exactly. A virtual laboratory where you can experiment and learn about how your machinery behaves under all sorts of conditions.
That sounds incredibly useful for optimizing operations and, proactively finding potential weaknesses. And it really suggests there's a huge amount of currently untapped potential within the data that mining operations are already collecting.
Absolutely. A vast amount of mining data currently just sits there, unanalyzed or underutilized. Machine learning has the capability to process these massive data sets in real time, continuously learning, refining its predictive models to prevent those really costly and disruptive failures.
Okay, so these aren't just abstract concepts then. Are there tangible examples of these AI-powered predictive maintenance systems actually working in mines right now? Real-world proof?
Oh, absolutely. There are some really compelling success stories out there. Take the Australian iron ore mine that implemented data mined AI.
Right.
Their system detected a developing issue in a pump bearing. Apparently, it had been missed by traditional manual inspections.
Hmm.
Because they caught it early, they were able to schedule the replacement during a planned maintenance window. The estimate was they avoided about $380,000 in potential repair costs and prevented 18 hours of lost production.
Wow. That's a huge impact from just one early detection.
It really highlights the power of these systems to sort of see things that might be invisible to human eyes or traditional methods.
Yeah.
And at another Australian coal mine, the same AI platform identified something called electrical fluting in a conveyor motor bearing.
Electrical fluting.
Yeah, it's a type of electrical discharge that can damage bearings, and apparently it's often quite difficult to detect through conventional methods. By addressing it proactively, they prevented unplanned shutdowns and significantly extended that motor's lifespan.
Interesting. More examples?
Yep. Then there's MineX, an iron ore operation using autonomous haulage systems. They used clustering algorithms and support vector machines, SVMs, which led to a 30% reduction in drill-related stoppages and a 20% extension in the lifespan of their drills.
Impressive gains.
Definitely. Goldstone Resources and their deep earth drilling use deep learning for vibration analysis. Result, 25% reduction in downtime, estimated $2 million in annual savings.
$2 million annually.
Yeah. Silver Peak Mining Corp used random forests, another ML technique, to predict conveyor belt failures, reducing unplanned halts by over 50%. And Deep Cave Mining Co's used recurrent neural networks, RNNs, to optimize their ventilation systems. That improved safety and increased productive mining hours by 20%.
So these aren't just marginal improvements. They represent really significant gains in efficiency, cost savings, safety.
Exactly, across the board.
These real-world examples are incredibly convincing. But it strikes me the effectiveness of these AI systems must be heavily, heavily dependent on the quality of the data they're analyzing, right? Garbage in, garbage out.
You've absolutely hit on a crucial point there. A successful predictive maintenance strategy is fundamentally built on a foundation of high-quality data. The data needs to be clean, it needs to be enriched with relevant context, and it needs to be well-structured.
Which probably isn't always easy to get in mind.
No, definitely not. And that's where specialized platforms like AICA come into play. They provide the tools and capabilities to help mining organizations cleanse their data, integrate it, organize it, basically make it truly usable for these advanced analytics.
Okay.
Because traditional maintenance approaches often struggle with this. They rely on those labor-intensive preventative schedules and fragmented monitoring systems where data isn't easily shared or analyzed holistically.
Right, the data silos problem.
Exactly. Solutions like DataMine AI, though, are designed to be implemented relatively seamlessly. Typically involves an initial assessment, figure out the key performance indicators, potential failure points, then integration with existing sensors, or maybe deploying new ones. The implementation time frame can actually be surprisingly rapid, often within, say, 4 to 6 weeks.
That's quicker than I might have thought.
Yeah, and initial insights can start emerging even sooner as the AI models begin learning from the incoming data streams.
So it's not just about feeding raw sensor readings into an algorithm. There's this vital stage of data preparation involved first.
Oh, absolutely essential. Data preprocessing. This includes tasks like filtering out noise sensor readings, can be messy identifying and handling outliers or just erroneous data points, normalizing the data so measurements from different sensors are on a comparable scale.
Yeah.
Then following that is feature extraction. This involves mathematically transforming that pre-processed data to highlight the most informative characteristics, the things the machine learning models can actually learn from.
Like pulling out the important signals from the noise.
Precisely. So with vibration data, for example, this might involve analyzing the amplitude of vibrations at specific frequencies, or the rate at which vibration patterns change over time. These extracted features are the key indicators of equipment health.
Yeah.
And finally, there's this growing field of explainable AI, or XAI, that provides techniques for interpreting the decisions made by these complex AI models, making them less of a black box.
Which helps build trust, I imagine.
Exactly. Increases trust and adoption among the maintenance personnel who need to act on these predictions.
This all sounds incredibly promising. But I can imagine that the challenging, often remote environments of many mines might present some unique hurdles. Limitations to implementing these sophisticated systems.
You're right to consider those challenges. Data quality and availability. They can indeed be significant issues in harsh mining environments.
How so?
Well, sensors can malfunction, obviously. Data sets might be incomplete because of communication dropouts. The data itself can be noisy, just inherently messy. You might lack good historical data, especially for newer equipment or newer operations. And integrating data from diverse, sometimes old legacy systems, breaking down those data silos we mentioned, that can be a substantial undertaking.
Makes sense.
And furthermore, while AI offers this immense potential, the interpretability of some black box models can still be a concern, impacting trust and adoption, like we said. Then there are the practicalities. Integrating new systems with existing operational technology, potential disruptions during implementation, addressing skill gaps in the workforce, ensuring different systems can actually talk to each other, interoperability, and of course, robust cybersecurity measures are all critical considerations. They need careful planning and execution.
Yeah, cybersecurity must be huge with all this connected tech. And it sounds like it requires a workforce that not only understands mining operations, but also has a degree of data literacy, some familiarity with these AI systems.
Precisely. There's a growing need for new skills and training. Areas like basic data literacy, understanding the fundamentals of machine learning, knowing the specific applications for mining equipment, the importance of effective human-machine collaboration, and definitely cybersecurity awareness to protect these increasingly interconnected systems.
And I suppose there might be some cultural resistance, too. Change can be hard in established industries.
Yes, we should acknowledge that, too. There can sometimes be a degree of resistance to adopting new technologies within a traditionally established industry, like mining. And finally, let's be realistic, the initial capital investment required to implement comprehensive predictive maintenance programs can be a significant factor for some operations.
Okay, so there are definitely challenges to navigate. We've talked a lot about AI and machine learning, but I know there are other important technologies playing a role here. Ultrasound was mentioned. How does that fit into the overall picture?
Yeah, ultrasound technology offers a really valuable and versatile approach to condition monitoring. It's particularly effective at detecting issues like excessive friction in bearings,
Okay.
compressed air and gas leaks, which can be a huge energy waste,
Right.
and even something called partial discharge in electrical equipment.
Partial discharge.
Yeah, it's an electrical phenomenon that can indicate failing insulation. So, in a mining context, where equipment failure can lead to substantial costs, especially in remote locations, ultrasound can be a crucial tool for preventing breakdowns. It also contributes to energy efficiency by finding those leaks, and it can help optimize lubrication practices, maybe reducing excessive or premature greasing.
And can ultrasound data also feed into the AI?
Absolutely, that's a key point. The data gathered from these ultrasound sensors can also be fed into AI algorithms. That provides an even more comprehensive, multi-layered view of equipment health. For example, an AI might learn to identify subtle patterns in ultrasound readings that actually precede more significant issues that vibration analysis picks up later. It creates a more robust early warning system.
Interesting. So what are some specific ultrasound tools or techniques commonly used in mining?
Well, one example is the on-track automatic regreasing system. It uses ultrasound to actually measure the friction levels within bearings.
Ah, measuring friction directly.
Yeah, and it provides remote, precise lubrication only when it's actually needed. It can even operate autonomously, and sometimes it can detect underlying bearing issues that go beyond just needing more grease.
Okay. What else?
For identifying compressed air and gas leaks, there's the UltraProbe. It's a widely used handheld device. It's designed to detect the specific turbulence and high-frequency sounds generated by leaks, even in really noisy industrial environments where you couldn't possibly hear it otherwise.
Right. Isolating that specific sound.
Exactly. And in electrical maintenance, ultrasound is invaluable for detecting that partial discharge we mentioned, those inaudible high-frequency sounds that indicate potential problems like arcing, tracking, or corona discharge in electrical components. Catching those early can prevent major equipment failure and serious safety hazards.
And these ultrasound techs are being applied pretty widely across different mining equipment.
Oh, yeah, absolutely. Think about ventilation fans, maybe deep underground. They can be challenging, potentially hazardous to access for manual lubrication. Remote regreasing systems guided by ultrasound are a huge benefit there.
I can see that.
Ultrasound is also routinely used to monitor transformers and electrical junction boxes for signs of partial discharge, helping prevent costly electrical failures. And on heavy machinery, like massive jaw crushers, automated lubrication systems that incorporate ultrasound sensors can ensure critical components, like the pitman bearing, are properly maintained, preventing premature wear and, again, that costly downtime.
Okay. We've covered a huge amount of ground, from the basics of PDM to cutting-edge AI, ML, and ultrasound applications. To kind of bring it all together, let's focus on a specific example, the Vaca Muerta region in Argentina. Our sources highlighted this area. How is predictive maintenance being implemented there, and what are the unique challenges it addresses?
Yeah, Vaca Muerta is a really compelling case study. It's a massive, unconventional oil and gas reserve, so slightly different from traditional mining, but facing similar heavy industry challenges. It has a unique set of operational and, importantly, environmental considerations.
Yeah.
It's a highly complex, geographically spread out operation in a demanding environment, and there's a really strong emphasis on sustainable practices. Predictive maintenance plays a crucial role there in minimizing leaks and spills paramount for environmental protection in such a sensitive area.
Right. Sustainability is key.
Definitely. And it also helps optimize the consumption of vital resources like water and energy, directly contributing to those sustainability goals and helping with compliance with environmental regulations.
And I imagine the economic incentives are pretty significant in such a large-scale industrial operation.
Absolutely. The potential for reduced maintenance costs, avoiding those really expensive emergency repairs in remote locations, extending equipment lifespan under tough conditions, savings on spare parts inventory, they're all significant economic drivers.
And you mentioned the high cost of downtime earlier.
Exactly. That figure, that downtime in industrial plants can average over $500,000 per hour. That really underscores the immense financial importance of effective predictive maintenance in a place like Vaca Muerta.
Wow. But the scale must present challenges.
Oh, yeah. The sheer scale of operations, numerous well sites, constant movement of equipment, it presents significant logistical challenges for monitoring and maintenance.
So how are they leveraging advanced technologies to tackle those challenges in Vaca Muerta?
Well, this is where we're seeing the emergence of things like AI agents and intelligent agentic workflows, systems like IAGN being explored.
AI agents, what are those exactly?
They're essentially autonomous software systems. They can automate various parts of the predictive maintenance process, capturing data from remote sensors, doing that initial data preprocessing, training and deploying the models, generating the predictions, and even suggesting specific corrective actions to the maintenance teams.
Automating the workflow.
Pretty much, yeah. For instance, there was an example of an LSTM model that's a type of neural network good for sequential data like sensor readings over time.
Okay.
It was implemented to predict compressor failures in a gas compression plant in Vaca Muerta. Reportedly achieved 92% accuracy.
That's very high.
Yeah, and it resulted in a significant 45% reduction in unplanned downtime and estimated annual savings of about $1.2 million.
Impressive results.
Definitely. But successful widespread implementation in Vaca Muerta, it still requires continued investment. You need robust monitoring infrastructure, you need specific machine learning models tailored to the unique operating conditions there, comprehensive staff training to use these new tools effectively, and really strong collaboration across different operational teams.
It sounds like Vaca Muerta is a really interesting microcosm of the broader trends we're seeing across mining and resources.
Right.
The potential of AI-powered predictive maintenance is enormous, but actually realizing that potential requires a strategic, data-driven, and collaborative approach.
Precisely. That sums it up well.
So, as we bring this deep dive to a close, what are the absolute key insights about the role of AI and machine learning in predictive maintenance for mining that you'd really want our listeners to take away?
I think the core benefits are just undeniable. Significantly reduced downtime, lower overall maintenance costs, extending the lifespan of very expensive equipment, and crucially, a safer working environment. We're really witnessing a fundamental shift, moving away from reactive and even just scheduled maintenance towards a much more proactive, data-informed, and increasingly sophisticated approach. An approach that allows for not just prediction, but potentially even prescription of the right maintenance actions at the right time.
It truly sounds like the mining industry is on the cusp of a significant transformation. It really makes you wonder, doesn't it? With all these advancements in AI, from optimizing maintenance to potentially enabling more autonomous operations, enhancing mineral exploration, even improving environmental management, is the mining vector entering a whole new era of operational excellence and sustainability, all powered by the intelligent analysis of data.
It certainly looks that way.
It's definitely a profound shift to consider. And of course, if you, the listener, are interested in learning more about any of the specific technologies or companies we've touched on today, folks like DataMind AI, AICA, UE Systems, Aveva, Razor Labs, they're absolutely worth exploring further.